Complex 2 is the succinate coenzyme Q reductase, but this is something that you guys may also remember as succinate dehydrogenase from the TCA cycle. It is the exact same protein. This also is a flavoprotein, so it does have that FAD covalently bound to it. It is 4 subunits, including 2 iron-sulfur proteins, and there are 3 types of iron-sulfur clusters, which are shown on the slide. All of those are just different ratios of iron and sulfur. Those are going to be coordinated then by cysteine residues. The overall reaction is going to be one of oxidizing succinate to fumarate and thereby reducing that ubiquinone to ubiquinol. In order to do this, succinate is first going to reduce the FAD to FADH2, which will then pass electrons through the iron-sulfur clusters, which will then eventually get them to the ubiquinone pool. So seen here, again, the electron flow is going to be from the bottom to the top, starting with the FAD. So succinate dehydrogenase is a B-type cytochrome. It has a non-covalently bound iron protoporphyrin. The iron can be in either the +2 or +3 oxidation state, and it can participate in 1-electron redox reactions. However, this heme is not in the direct electron transfer route from the iron-sulfur clusters to ubiquinone. From what I was seeing, the research is still being done on exactly what this does. There's a couple of really interesting pieces, but for the purposes of our course, we are just going to focus on the fact that the electrons are going to go from FAD to the iron-sulfur clusters to ubiquinone, and the heme is there, we'll call it for stabilization purposes. There's actually no translocation of protons across the membrane in this particular molecule. Protons are going to be needed in the reduction of ubiquinone to ubiquinol. That still does require proton uptake out of the matrix, but there's no pumping of protons in complex 2. Partially for that reason, succinate is going to make a smaller contribution to making ATP than we saw with NADH. Before we move on to complex 3, there is another process that's going to add to the ubiquinone pool. Fatty acyl-CoA dehydrogenases will also be donating electrons and reducing that ubiquinone to ubiquinol. These are actually soluble matrix enzymes that are involved in fatty acid oxidation. So these aren't membrane bound, but they are in the matrix of the mitochondria. And what's seen here is that dehydrogenase reaction. And again, emphasizing the fact that this reaction is going to involve reduction of an enzyme-bound FAD. So these are also flavoproteins. And just a reminder that that FAD is in brackets to show you that it is bound to the enzyme. And that is going to be what then supplies electrons to that ubiquinone pool. Complex 3, electron transport from our coenzyme Q, again that's that ubiquinone pool, to cytochrome C. This is also known as the ubiquinone cytochrome C reductase. So if you guys have noticed, there are a lot of alternate names for these enzymes, and that's mostly to keep in mind of what they do. So in this case, they're talking about the fact that it's going to take electrons from ubiquinone, well, in this case, ubiquinol, to cytochrome C. So that coenzyme Q, again, that's our ubiquinone, ubiquinol. Ubiquinol is going to pass electrons to cytochrome C and pump protons in a unique redox reaction, which is going to be known as the Q cycle. We'll get to that in just a minute. This is then going to involve a transmembrane protein, which will be a B cytochrome with its own hemes. These cytochromes are also going to be 1-electron transfer agents. And to remind you that ubiquinol is that lipid-soluble electron carrier. So we've been looking at it as being something that's embedded in the membrane itself. Cytochrome C, on the other hand, is water-soluble. So what's happening here is complex 3 is taking electrons from the ubiquinone pool that's in the membrane, in the inner membrane of the mitochondria, and then transferring them to cytochrome C. Cytochrome C is then going to transport these through the matrix to complex 4. For the Q cycle, we are going to break this into 2 halves. The main reason why the Q cycle is a little bit strange is because it's going to involve multiple molecules of coenzyme Q and multiple oxidation states of that coenzyme Q. But what's going to happen first is ubiquinol, so remember that's the fully reduced form of coenzyme Q, is going to bind to the QP site. Once there, it's going to be oxidized, so it's going to basically release the electrons that it has in 2 1-electron steps. Those electrons aren't going to go to the same place though. So it is going to release the 2 electrons it has One of those is going to be transferred to the iron sulfur cluster center. That then is going to go to cytochrome C. So the very first electron that ubiquinol gives up is going to go to cytochrome C via iron sulfur cluster centers. As this happens, then 2 protons are released. So now we actually have those protons moving into that inner membrane space. The other electron is actually going to go to cytochrome B, cytochrome Bl, and then cytochrome BH, and it's going to be reducing another molecule of our coenzyme Q. So what we have at this point is we have one molecule of our coenzyme Q that came in, dropped off 2 electrons. So that went from being fully reduced to being fully oxidized. Then a second molecule in the Q site went ahead and received one of those electrons. Now what's going to happen is we're going to have another molecule go into that QP site. So we're going to have another molecule that's going to be oxidized again. So we're essentially doing the same thing we did before. So we have a new molecule of ubiquinol that's going to drop off its 2 electrons to our complex 3. The first electron is again going to go through iron sulfur clusters and again go to cytochrome C. The second electron is going to do the same thing it did before. And that second electron is going to go through the 2 different cytochromes to wind up finally reducing our other coenzyme Q molecule. So remember that we had left this bottom in the QN site, this bottom molecule, where it had gained a single electron but still had room for one more. So that bottom molecule of coenzyme Q then picks up its second electron. As it does that, it then is going to abstract 2 protons out of the matrix of the mitochondria. And don't forget that when we went ahead and oxidized that molecule at the very top, as that oxidation was taking place and it was dropping off its 2 electrons, there's also 2 electrons then that are going into the inner membrane space. So to summarize all of that, what happens is you get 2 molecules being oxidized, one winds up being reduced. So there's 3 different molecules of that coenzyme Q being involved here. 2 molecules of cytochrome C are reduced. Those are 1 electron transfers. 2 protons are consumed in the matrix, and 4 are released to the inner membrane space. This is a look at the structure, again, mostly just to show you that there's some parts of this that are in the membrane, some that are in the matrix, some that extend into the inner membrane space.